Ok, buenos días a todos. Good morning, everyone. Como tenemos gente de otros países que no son de habla hispana, como hemos hecho anteriormente, voy a cambiar a inglés un rato. Entonces, so good morning, everyone. Thanks for joining us. We're continuing our webinar series on Biomass, our Biomass 2020 webinar series. This is as I said the last time, this was an event that we were gonna have in July, in August, but it couldn't happen because of the pandemic. So we've decided to have this. This is a webinar series that we're having every month. First, we had Dr. Robert C. Brown from Iowa State University. Today, we're having Stefan Junne from Germany, and next month we're going to be having Dr. Borja Velasquez, who recently joined in the project. We also have a call for papers. We're going to be having a special issue on biomass this December in our journal, and very briefly, Juan Sebastian, one of our professors, will be showing how to where the link is to make a submission. So today we're going to be having this talk during about 45 minutes. And then the questions, you can be making them in the chat. And also at the end of the talk, we're going to have a round of questions and answers. So we're going to be formulating the questions that you wrote in the chat, or you can make your own questions directly after the talk. Okay, so just for those of you who don't know us, this is an event that we had initially in 2017. So this is our second edition. And we, as organizers, are the Institute for the Development of Alternative Energies and Materials at Universidad San Francisco de Quito. We have these 3 different research lines, which are bioprocesses, biomaterials, thermochemical processes. I'm not going to go into details because of time issues. So if you have any questions, or if you want to know more about us, you can visit our website at the university main website. So I'm going to give now Juan Sebastian. Will you please show us where the link is to make a submission for the special issue?
Okay, thank you, and welcome everybody. I'm showing on my screen how to access the website so you can submit your papers. I'm going to give you a link so you can come into this page, and basically what you do is click on this button here that says basically send your article, enviar un artículo. Hit that, and that page brings you to all the details on what to include in your paper, so you can review those. And on the top of that page, you can click again on this send an article, realizar un nuevo envío. You click here on your left, and then you're going to be prompted to this page. You choose the language that you're going to be using for your publication. Here you can either choose Spanish or English. And then for the section, and this is very important, you should choose Biomass 2020. And that'll send your paper to the special issue so we can start the reviewing and all the process. So that's basically it. So pretty much simple steps to follow, and we can receive your paper. So we're going to be publishing these later this year, and yeah, we're going to be looking forward for your paper. So thank you very much, and you can go back. We can go back to Jose.
Right. So now we're going with Daniela, who's going to be introducing our speaker today.
Thank you very much, Jose and Juan Sebastian. I want to introduce our speaker today, Stefan Junne. He has studied between 1997 to 2003 at the University of Erlangen-Nuremberg and Northwestern University Chemical Engineering. In the year 2003, he obtained his diploma as a chemical engineer. Between 2004 and 2009, he worked as a research associate at the Bioprocess Engineering at the TU Berlin. From 2009, he obtained his PhD with the topic of dynamic metabolic flux analysis and modeling of the acetobutanol ethanol fermentation. And since 2010, Stefan is the group leader of Bioprocess Engineering Department of Biotechnology at the Technische Universität Berlin. And he's currently leading the group's process analytical technologies and smart bioproduction grids under the leadership of Professor Neubauer. His main fields of activities are the process analytical technologies to monitor the liquid phase and single gas to liquid to industrial scale, multi-position and multi-parameter monitoring, feedstock pretreatment, scale down and scale up, modeling and life cycle assessments, as well as his focus is on development of holistic concepts for energetic and material use of biogenic raw and residual material for a circular economy between basic research and applications. So with this, I give the introduction to Stefan. Thank you very much for accepting our invitation. We are very happy to have you here and to learn the interesting work that you're doing at TU Berlin. So please, you can start with your presentation.
Yeah, thanks a lot, Daniela, for the nice introduction. I think I put a lot of words in there. Basically, we try to make more and more valuable bioproducts or products out of whatever we will get. And this is also what the talk is about. I will share my screen. Okay. Yeah, as Daniela said, I'm from the Technische Universität Berlin. We are basically dealing with a lot of bioprocesses. Among them, anaerobic digestion has always been an important one. But I maybe have to say 2 sentences about the history of anaerobic digestion in Germany. It might be a little bit different from the situation in Ecuador, as we experienced a vast increase of anaerobic digestion plants between the year 2005 and the year 2012, 13. Due to state tuition. There was a new law, we call it Renewable Energy Act number 1, that was put in place in 2005, which allowed farmers to get state support for building a biogas plant. And at this time, it was about being very fast with the implementation of biogas plants in order to get as much money from the state as possible. It was not the aim to build the best digestion plants ever, which led us to the problem that we have nowadays. Several of, not all, but some of these over 9,000 plants that are not running so well. And this got some criticism. Like 5 years later, after this act was initiated, people said, is this so efficient? Is this so sustainable? And there was a lot of criticism about anaerobic digestion. And nowadays, we are back in a situation that people see anaerobic digestion as an important part of a circular economy, which is now, you probably all know also these Friday for Future movements. This is rather strong here in Germany, which also pushed a little bit the politicians toward really taking more care about biogenic residues. And this also led in our research field to, I have to say again, to more intensified action on this field. And yeah, especially the flexibility. This is a big difference to what we had in former times. The flexibility of feedstock utilization, which means you should be able to use all what is there. and not just the fruits of a crop. That has become much more important nowadays. And this, my talk will be about this. I will show some examples which are related to our research, but I will also show some challenges which we are still facing if we want to just integrate better anaerobic digestion plants into existing local carbon or whatever material streams. Phosphate became also very important within the recent years in Germany, for example. It's not all about carbon, but mainly carbon. And of course, we can then discuss also after the talk. Yeah, we are here in Germany and everywhere in the world talking a lot of bio-based economy, but actually we are of course far away from it. We do not have yet truly sustainable production, as many products we use in our daily lives are originating from crude oil, which is here in Western Europe even more crucial since we do not have many sources. Now when the UK will leave the EU, we actually do not have any reasonable resource for crude oil. The transportation of it is difficult, costly. Actually, we are facing big problems with pipelines in Russia because the earth is melting and the pipes are breaking, and there is a huge environmental impact by the oil that is flooding large areas in Siberia. So that's a big problem. And Germany has already since more than 10 years has a bioeconomy strategy, which tries to replace, for sure not all, but more and more products away from crude oil derived products to products that are made out of renewable sources, which are and this would be the ideal case, which are made of side streams, which are there anyway. We have huge dump hills of side streams from agricultural activities. I will show a few examples later on. And these products should then penetrate many sectors of our daily lives. One example is bioplastics. Also, it's a difficult one because plastic is a very cheap product, but we have also other products. I will show also one example later, which is has a higher value, which is nowadays also not made very sustainable and which can or is already being replaced partly by a bio-based product. So the penetration of products is envisaged. And I have to say, you can always say it's not a good situation, but when I see the development within the last 5 years, at least in Germany, I have to say a lot is now changing and will likely change even more because also the mindset of many people have changed in the past. But this means that we also need to have the bioproduction processes, which we eventually just do not have, or they are not efficient and they are too costly. And this is the big challenge we are facing right now. So I was already talking about feedstock flexibility, which we need. You all know the discussion about bioethanol we had in the world when it was about competitive production of crops for either having them as food or having them applied as bioethanol. We call it here in Germany the tank or dish discussion, which changed even the plan the federal government had in Germany. They wanted to replace petrol by 30% of bioethanol, and they stopped this. And nowadays it's only 10% of ethanol. So they reduced their own goals due to this discussion because there was a lot of criticism by the land use for renewable crops for making petrol which is just burned. So in order to achieve true sustainability for such processes, we need to step away from these crops, especially the fruit bodies, to have them as feedstock, and we need to replace them at least to a big amount by side streams, which are not directly compete with the food application. So we have a lot of them. Actually, this is more relying on Central and Northern Europe. We have from the forest activities, we have a lot of bark material that remains unused. If you think of bark, that is a hard material, lignocellulosic material, it's not easy to digest. So this is also a challenge, but there is definitely a lot of it there, which is also very cheap. Same for sawdust. In the agricultural sector, we have a lot of manure from the pig and cow farming. We have all material that is side material from the so-called energy crop production, which we are not using very efficiently sometimes nowadays. And we have a lot of straw. We have municipal wastes, especially food waste, which is used for anaerobic digestion frequently, but probably there are other ways, I will refer back to this later, other ways to use these food waste than just dumping it into a biogas plant. We have the sewage sludge, which is becoming more and more challenging because the wastewater treatment plants are forced to take out more and more valuable material there. But we also have from the industrial processes, we have a lot of byproducts that are not used. And just think of baker's yeast production. So we have here in Germany, we have a lot of baker's yeast production, and only the yeast is used and the rest is just thrown to the wastewater treatment plant. Also, there's still a lot of nutrients in there. Oops, sorry. So our focus is now mainly not in terms of anaerobic bioprocesses, is not so much on this final step here, but it's on the first step we have in all these processes, that's the hydrolysis. Hydrolysis means the breakdown of any material by certain means. Here I'm talking about microbial hydrolysis. So the microbes produce enzymes, and these enzymes degrade the feedstock, so to say. And we put this now more and more in the center of our research, because right now this is all done together in anaerobic digestion plants. There is no separate stage of the hydrolysis, which means that there's always a compromise of the process conditions, because you do not have only, if you think of biogas production, you do not have only hydrolysis, you have also other steps. I will refer shortly later to that. So if we do not have a separate hydrolysis, we cannot optimize the process. And to my opinion, this was a long time neglected. And now people are getting more sensitive to this step, because this step allows to use a wide variety of different biogenic residues to use for such a microbial bioprocess. And also, I will refer to this also later in some examples. If you stop this hydrolysis at the right time, you need not necessarily to get to biogas itself. You can use the intermediate products that are there to produce other goods, like even food and feed additives, bioplastic I already mentioned, and also some others. So now going a bit back to the basics about traditional anaerobic digestion. So we have the hydrolysis, as I already mentioned, as the first step. Then these hydrolytic bacteria convert and break down long chain carbohydrates mostly, but also proteinogenic sources to shorter chain lengths, which are then converted by acidogenic and acetogenic bacteria Acetogenic means they can produce a broad spectrum of acids. Acetogenic bacteria only produce acetic acid. They break down these to these, some people call it volatile fatty acids. For me, they are short chain carboxylic acids. So beside acetate, it can be lactate, it can be propionate, butyrate, quite broad spectrum. And in a biogas plant, these acids, especially then acetic acid, is converted to methane by methanogenic organisms. So this is the traditional way of having such a biogas plant. But as I said, this hydrolytic stage is often not conducted well because it's conducted with all these other steps. And these are totally different bacteria. And here the methanogens are not necessarily bacteria, even other organisms. They require different growth environments. And this is then neglected if you do all at the same time. The hydrolytic bacteria might need oxygen to be more efficient, not much, but a little bit as cofactor. They might need to adapt to certain feedstock. So if you change the feedstock from a carbohydrate-rich feedstock to a more protein-rich feedstock, then these hydrolytic bacteria have to adapt. The other ones, they don't have to adapt because they will get the same intermediates. But the hydrolytic ones, they have to adapt. But how should they adapt when they are part of a whole consortia with all the other organisms? Even they are forming agglomerates. So like biofilms, just in a round form, they cannot easily adapt themselves because the old ones will be there. The new ones cannot grow as efficient as possible. So adaptation to different feedstock is really hard. This is why most of these more than 9,000 biogas plants in Germany run with a stable feedstock throughout the year. Although there would be cheaper feedstock available for a month or two, the operators rely on the same feedstock because they fear that their whole process will be disrupted and heavily disturbed at the end. And what is also not considered in this concept is a microbial overload you could get because you're adding feedstock, which is of course not sterile. It would be too expensive to sterilize the feedstock. So the feedstock as such already brings a lot of microbes in there. If there are some microbes which are more flexible, then they will overgrow the hydrolytic bacteria that are in there, and then you get a disruption of the whole process. And then the methanogenic organisms, they are the, let's say, weakest ones, so they are very sensitive to changes. They might then not act appropriately anymore, and then you get also a disturbance, especially if you will change the feedstock. So if you would have a separate hydrolytic stage, and you see that something goes wrong, you just stop the flow to the other parts, and then you can react directly there, and the other parts will not heavily disturbed, at least if you can solve the problem within a week or so. So we believe that the separation of this hydrolytic bacteria is one mean to increase the flexibility of anaerobic digestion processes in terms of feedstock utilization. So what does it mean? This would mean that such a traditional biogas plant setup, so this is representing 90% of the biogas plants we have here in Germany, would need to change, because usually you have here one main digester, that is your fermenter 1, then you have a post digester, that is fermenter 2, and you just dump in here the biomass. So if you would separate the hydrolysis stage, it would mean that you will add here another reactor that does not necessarily look like this one. Here it can be a little bit smaller, it's faster degrading anyway than this process here. Usually you have here mean residence times of 30 to 40 days. So we are talking here about long residence times. You could have your smaller reactor in front, which has a residence time of probably 10 days, where you add the biomass in advance. The biomass is degraded already to intermediates, and then you feed the intermediates to this fermenter here, where it's then converted to other intermediates, mostly acetic acid, and later on to methane, for example. That's not too much. If you see all the other parts you need here, so all the gas streams for drying the gas, for burning the gas, if you want to make electricity out of it, the heating concepts to use the heat, because 50% of the energy from methane when you burn it is distributed as heat. You can heat up stables, for example. This is a common concept in Germany, especially in winter times. You have all these installations, and you just would have to add here one small reactor with not much instrumentation on it. So it's also not so expensive. How is it done today? Well, we have in the area of municipal waste utilization, we have kind of sorting here. You see how that usually looks like, with a lot of plastic bags inside. I saw similar things in Ecuador as well. So there's the pre-treatment is selecting, cleaning a bit, and then this is just like it is. It's dumped into the biogas plant. In terms of more agricultural side streams, we have here, for example, straw, which is now becoming more and more important as a relevant feedstock for anaerobic digestion. We have mechanical pre-treatment. You see here hammer mill, for example, that was one of the first plants in Germany that used straw throughout the year as feedstock for anaerobic digestion. So the fibers of the straw are crushed down. They are not shortened by this hammer mill. It's just so that the fiber structure is mechanically harmed, so to say, so that the surface for enzymes that can degrade later on the straw is increased. Yeah, but still there is no separate hydrolysis stage. It's dumped directly into the digester. Since the digestion takes then longer than, for example, the digestion of maize, you have also longer residence time, and the reaction time for the digestion process. For example, if there is a disturbance, just then also takes much longer. So it's already more risky to use such a feedstock because if you have, for example, acidification, which means you have an increase of the acid concentration so that the methanogenic organisms are harmed, it's very hard to actually react, because if you stop feeding new material, it takes days until you see a reaction on the acid synthesis. So here, it's a good attempt to use straw because it's a side product in massive amounts in Germany, which is creating also then a methane emission to the atmosphere, which has some relevance for climate change. So it's much better to digest it in a closed vessel, but yeah, it's just taking too long. So what can we do in order to simplify the utilization of such feedstock? So one thing actually we are doing now, which is quite successful, is using ultrasound. Ultrasound in a bypass, you see here that should be just a digester, where we have here a bypass where the whole slurry is pumped through. And then here is a plate inside and a sonicator, which implies ultrasound here in that tube, which has usually a residence time of a minute or 1.5 minutes, so to say. So it's not that long. So you can, although that is a small tube here, since it is a continuous process, you can pump quite a reasonable amount of that huge volume through this part here in a reasonable time. But the problem is that, so this technique is used now for some years in Germany at some plants, and at some plants it's really successful, and some plants it's not. Why is that? Yeah, well, you have different feedstock composition, you have different degrading potentials in these anaerobic digestion plants, and you need to set the energy input of that ultrasound to a certain value so that it changes something in the anaerobic digestion without wasting energy. Yeah, because usually also for ultrasound, the more power input you have, the more effect you will get. Yeah, at least, I mean, if this is starting to boil because you put so much power in it, then you should probably stop. Yeah, then it's for sure too much. But in a certain quite wide range, you just don't know the settings. You don't know whether the energy input of the ultrasound is sufficient or not. And you should not apply more than what is necessary. Now you can ask, well, I will see it in the gas composition. I will see it in the amount of biogas that is produced per time. But remember, we were talking about 30 to 40 days residence time. We have a rule of thumb that you will need 3 residence times to see a certain change. And then you need to repeat the experiment probably 2 or 3 times. So we are talking about 1 year to evaluate one set point. So we probably talk about 10 years to fully evaluate with an experimental plan the specific settings of an ultrasound in power input for a specific feedstock. So this is not doable. So we need to find a solution how to measure this very quickly. And what we just recently did in a project was that we modified together with a partner and applied laser light back reflection measurement. That is an interesting technology as it allows very highly energetic light beam to be put directly on the cultivation broth, which you probably have seen. This is a brownish, very dense material. This here is a rotating optical device, which means that you will obtain a pulsed laser beam, but not the whole laser is pulsed. That would crush the laser very soon, but only the light beam is pulsed. And if you have a pulsed light beam, you have a time where you apply light on your sample, and you have a time where there is no light applied, but a back reflection occurs. And if the light is highly energetic, then even in such a culture process like we have it in anaerobic digestion, something is back reflected of the light. And this, if you have a very sensitive sensor, can then reliably measured. And by this, we can measure particles directly inside such a digester, which allows us then, you see it here a little bit, to estimate the size of such a particle, because we know that if we have this here as back reflected light and we have it in this distance, then we know that the surface of the particle is quite close to this distance here, because at the edges there will be only very low reflectance, and beside the particle there will be no reflectance. So by this, we do not get only the particle number, we get the particle size. And we also would get then the particle size change of an ultrasound device. So we see here the change of the particle size in just a natural digestion process. So this is actually what hydrolytic organisms can do. So this is some of the particle distribution, which starts here at 0.5 micrometers and ends up in this case at 530 micrometers. So this is somehow the particle range where we start. A lot of particles are here in between this range of 3 to 30 micrometers or up to 90 micrometers. And after hydrolysis, in this case 120 hours, we see that we have a much more narrow range of the particle size distribution. So the particles within this size here, so from 11 to 12 micrometers on, they did not disappear, but their portion went down quite vastly. So now the major particles are here between 3 and 6 to 7 micrometers. These are, by the way, the organisms, because they also have a particle size. And these other particles, which were from an undissolved feedstock, were degraded here. Of course, we usually have much bigger particles in, but this was now just a slide from a sample where we did not have these very big particles. We usually measure up to 20,000 micrometers, so 2 centimeters. We are looking at the degradation potential. So here we see a maze, which is here, what is this, 2,000 micrometers, so 2 millimeter big fibers, quite a huge portion out of it. They're there, and they were degraded, in this case, with ultrasound now. So this is not a natural digestion. So this is the degradation you will get if you put an ultrasound into this digestion broth, in this culture broth. So the particles that are in this range are getting much smaller through ultrasound. You have a shift here from these 2 millimeters down to 50 to 60 micrometers. Again, here we have in the core, we have the microorganism fraction. That is changing a little bit because of course, all particles are getting a little bit smaller. So you can say the untreated blue bars here represent the microorganisms that were in there. And afterwards, this fraction constitutes of microorganisms and some particles that were broken further down. So, but if we look here at this region, we have a huge change from the original state, the blue bars, to these yellow bars after the ultrasound treatment. So here a lot of particles went into this range. And this is exactly what we use now to justify whether we, to examine whether the energy input of the ultrasound is a correct one. If we wouldn't see here any change in this range, then we can say, okay, the ultrasound is not degrading any particles. So it will probably also not have an effect on bigger particles, which will probably not get much smaller, but the surface will get more holes inside so that the enzymes of the microorganisms can degrade it faster. And on the opposite side, if we see that a lower energy input already causes this change here, then we do not need to increase the energy for the ultrasound treatment. So such a particle size measurement can help us a lot. Of course, we are working with the bioprocess, so we have to evaluate this not only the power input, not only based on the particle size, but we have to relate the particle size distribution to the anaerobic digestion process itself. What you see here, I'm not sure, it looks a bit weird now, that slide here on my screen. I hope you can see it a little bit better. We have here the CO2 production within the first 24 hours in batch digestion processes. So there we just dump in an inoculate together with feedstock. And then we had different ultrasound pre-treatments, and then we measured the CO2 production within the 21st hours. Because this tells us something about the degradation efficiency of the microbes, because the microbes only produce CO2, then they have feedstock that they can digest itself. And we saw here, if we use the change of the D50, so the average particle diameter between 20 and 200 micrometers, so the change we achieved by using ultrasound, we saw a direct correlation to the CO2 production. So the bigger the change of the D50 within this fraction of 20 to 200 micrometers for my silage, the bigger was the CO2 production afterwards. So we know that the particle size is a sensitive parameter for setting for the setup of the ultrasound. We can use this also for other applications with more like even cellulosic components, even chemical treatment. So it does not need necessarily to be ultrasound. We can use other mechanical pretreatment methods, or here in this case, it was a chemical method, where we saw that we changed the particle size a lot from this was unpretreated material and this was treated material. Yeah, and again, when you see the fraction from 20 to 200 micrometers, the D50 would have changed here vastly. Yeah, so this was also an efficient treatment, and this is sensitive then also for anaerobic digestion. What we also do is always having a look at the viability of organisms, because not only the let's say pre-treatment and the feedstock range is very important, but also whether the organisms feel good in such an anaerobic digestion process or not, because they should basically do the job. And if we see difficulties in using different feedstock, for example, somebody should use a feedstock he never applied before in his anaerobic digestion plant, he probably will only see issues after several months of operation, and then it will take at least the same time to recover for the process. So that can lead to huge losses, financial losses. In order to see that earlier, we should have a look at the viability of the microorganisms. So now I have here big background noise. I don't know what people are doing here sometimes late in Friday afternoon. Sorry about this. So we should have a look at the viability and vitality of the organism. How can we do that in such an undefined culture we have there? There's basically everything in. We have one method which we have developed with a Berlin-based company several years ago, which turned out to be quite successful. We use the culture first, we wash it a little bit, so we separate a little bit, especially the ions that are in there, so that the cells and whatever undissolved material remains. And then we put all these cells into an electrified chamber. And there, if their cells are viable, if the membrane is fully intact, if ion channels that are very important for the transport from the inside to the outside of a cell and vice versa, if this is all working well, then these cells are behaving like iron in a magnetic field. So they orientate to a certain direction, and the speed of orientation tells us how well they are feeling, so to say, with the current feedstock. Long time before we see any effect on the gas composition and so on. And then this is what we get. If the cells are in this chamber, we get this reaction here. That's a change in the orientation. We can measure it just by optical methods. So because the light beams then are one time more absorbed and the other time less absorbed. And the time it takes to get to this new steady state, this is what we measure. And then we are getting these spectra here because we can apply different electrical frequencies. And let's say it shortly, the higher that value is, the better it is. So here we have difficult to degrade feedstock, an unadapted culture. You see here very low values in comparison to this one. And these are batch digestion processes. So we added once the feedstock and then we let the organisms degrade it. And here you see this polarizability, we call it, which we measure of the organisms. It goes up very quickly within 1 or 2 days because the organisms can degrade the feedstock very efficiently, very quickly. They feel very well. Nothing is missing. Yeah. And here they are just done. So there's no new feedstock. Usually in an industrial plant with the continuous operation, we would have added here more feedstock, but here we just didn't add any feedstock, and we see, okay, then it goes down again because just feedstock is lacking for growth. But here we never reached such a value because here the degradation also took place, but it was totally inefficient. Yeah, we can relate this then also to a prediction of the methane production and so on. But this is not even the most important thing here. The most important thing is that we can distinguish between a good and a well-adapted culture and a non-well-adapted culture. So I was already talking about the pros and cons of biogas. So I can also, given the time that is left, very short. So we said here in Germany, well, just burning always biogas, it's probably a waste of the feedstock, because the energetic use is the lowest in terms of cost, the lowest use you can have. There are many things that can be made out of all these feedstock, which has higher values. What we actually do now is we are using dark fermentation, where we skip this phase here of producing methane. So we just end here at the short chain carboxylic acids. And with these organic short chain carboxylic acids, we can make a lot of it. So feed, food, bioplastics, biosolvents, as I said before. But what we are doing now is, and we are applying either a high or low pH, where the methanogens cannot be active at all, but we achieve by bioaugmentation, also coupled to this viability measurement, we achieve a very active culture, an acidogenic culture that produces acids. And then we use these parallel flasks here with gas measurement on site, where we either use CO2 and H2, or sometimes CO2 and methane, just as a control of the methane, that we really not have any methane production here. We use this, and we make batch digestion experiments to find suitable conditions to get as much acids out as possible, because we are always competing with biomass formation. The organisms want to grow, but actually we don't want to have them growing so well. We want to have them making a lot of acids. And then we couple whatever is coming out here. We couple, and I will show very shortly one example, we couple this to the production of long-chain polyunsaturated fatty acids for fish feed production. And therefore, we are using plug flow digesters, where we have here kind of separation of the hydrolytic phase, as I explained in the beginning. So we don't use a separate bioreactor for this, but here we have a phase that is well suited for the hydrolysis. And here we have then the acidogenic phase, where the organisms form the acids. And we monitor a lot. We are basically monitoring the gradients along this plug flow reactor in order to control the process. So, and going now to the product we make out of it then in a subsequent sterile process. So then we are not talking anymore about anaerobic digestion. The process then is sterile, is a monocultivation process. We use these short chain carboxylic acids to produce this polyunsaturated fatty acid in order to replace fish oil. Fish oil is nowadays used a lot in aquaculture, especially in Norway, in Europe, but also in Latin America and Asia. And we want to reduce the use of fish oil, because fish oil is used from small fish that is caught in the ocean, and then this fish is lacking for big fish as a food. And we are using heterotrophic algae, and you can see here in this picture, you can see these droplets here. This is the accumulation of this polyunsaturated fatty acid. And we use then the short chain carboxylic acids from the dark fermentation to produce this long chain fatty acids in this algae. And by this, we are getting a much higher value addition out of the feedstock. And of course, we all want to do this under flexible feedstock utilization, to have like these closed cycles where we have the food waste, which we use for the dark fermentation, and then we make fish feed out again, where fish is produced, which then comes again on our table, on our dishes, to be consumed as food. So this is the whole idea behind. So I think I can skip this last slide because I summarized in between. Also, the time is running. So if I had more, if I had more time, I had shortly say something to our department, because we are not only dealing with anaerobic digestion, but if you have questions to this, feel free to ask now. And otherwise, I thank you a lot for attending here. Many thanks for the organizers. And yeah, whenever you have questions, feel free to ask.
Thank you very much, Stefan. So if anybody has any questions, si alguien tiene alguna pregunta, we have a first question here from Antonella. It says, approximately what is the potential of electricity that is generated from biomass sources that you mentioned? For example, straw.
Straw, if digested correctly, it's similar to maize whole plant silage and similar to grass silage. It just takes longer.
Okay. We have another one here from Adrian. I was conducting a study on the use of rice husk as a biofuel. My question is, the anaerobic process or pyrolysis, which has better advantage to take? Which one has better advantage? We have in Ecuador 300,000 tons by year. If only a third is used, it is important one.
Ah, that's a hard question. Yeah, so I know that here are some people that are working a lot on pyrolysis, and I would honestly, I'm a chemical engineer by training, so I'm open to any of these technologies. Right now, the situation is so in Germany that many people wanted to use pyrolysis for 20, 30 years for many things. It's just not working so far due to several reasons. So we are right now much further or nearer to the application with anaerobic digestion. Also, rice I would see rather for mono or a co-cultivation process and not for undefined mixed cultivation. But it will probably change in future. So if pyrolysis will be more and more applied reliably and cost efficiently in practice, it might be better for some feedstock. And then we have to see, and probably not for manure, because there's also a lot of phosphate in, and this is for sure. There was so many money used up for recovery of phosphate in pyrolysis for sewage sludge, for example, but also others. I think we can do here much cheaper, more with the bioprocess. But yeah, you always have to see the whole network where this is integrated in order to decide whether pyrolysis is better or a microbial bioprocess is better. Also, a combination of both could be doable in a biorefinery concept.
Great, thank you. There's another one. It says, is biogas as commercially competitive as petroleum gas, like natural gas?
Yeah, that also depends on the country you are looking at. Seeing it here as in Germany, we have to see that the petroleum in Germany is used for a liquid fuel. And here we are talking about a gaseous fuel. And we are not having the portion of gaseous driven vehicles in Germany is like, you can forget it. Yeah, it's nearly nothing. In Sweden, for example, it's different. In Sweden, the public transport is driven by biogas. So there you have a competition. And in Sweden, the taxes on petroleum are so high that it is the best thing for the companies is to use the public transport, which is owned by towns, and the waste collection is owned by towns. So the towns are producing their own fuel for their public transport, which is mainly relying on buses there. So for them, the biogas is then cheaper than the petroleum. So it's also a hard question to say. I don't know for Ecuador. I know for Germany, the petroleum here is cheaper than the biogas because the biogas gets state support. But we are introducing a new tax in Germany. It's about CO2 emission. And this is increasing within the next 10 years. And then there will be a break even. There would be then biogas cheaper than fossil fuel-based petrol.
Thank you, Stefan. I don't know if there are any other questions.
Yes, the one from Fernando Nicolas Vela. You can read it.
Oh, okay. Sorry, I didn't see that. Is it enough to use cellulosic biomass to make environmentally feasible this process, considering the high demand of natural gas?
This also, again, sorry if I'm always answering the same, it depends on the country. For Finland, for example, they can produce much more than they would need. We here in Germany have also actually a lot, but it would not be sufficient to replace all. But we have to see this locally here in Germany as well. So we have areas where we can cover the gas demand for like the heating in the houses and so on. We can cover by using lignocellulosic side streams. This is not true for the big cities. There, it's definitely a mismatch. But we have to see, we have now several concepts of moving away from any fossil-based source. So this includes natural gas, which we obtain right now from Russia. We have strategies for making hydrogen out of windmills, for example. We have a lot of windmills here in Germany. Actually, the energy generated by the windmills is more than we can sometimes use here in Germany. So then now there is a big network strategy driven by the government to install huge capacities to make hydrogen out of these windmill and this electricity from windmills. Then we have now strategies even to couple this, because storing hydrogen is very expensive, to couple this with the bioprocess with methanogens, which can convert the hydrogen into methane. So if you then couple the lignocellulosic based conversion with such an attempt, because you need some biomass, you need the methanogens, then you can cover the gas demand in Germany. So it's not only the biogas process as such, it's coupling the lignocellulose as co-feed together with the hydrogen to get methane that in amounts that are sufficient to cover, not tomorrow, but maybe in 10 or 15 years, more or less the demand in Germany.
All right. So we have another question from Alex. It says, how efficient are those bacteria, the ones that you talked about, compared to others like indigenous bacteria from the Paramo, which are the highlands?
Oh, I didn't get the last sentence.
He said, how efficient are the bacteria you talked about compared to other bacteria like indigenous isolated from the Paramo, which are like the highlands in the Andes? So I guess it would depend on, you would have to.
This I don't, sorry, this I don't know. Yeah, so this is, what is possible today is bioaugmentation. For example, the method I showed you about the viability, we use it also in bioaugmentation. Bioaugmentation means we do not want to have just a random composition of microbes, but we want to add certain types of microbes so that they get the dominant part of the digestion process. And by this, again, they need to feel comfortable. Otherwise, they cannot get the dominant part of it. So what we do is we actually make very bad conditions for the consortium we have. Then we suddenly change to better conditions and at the same time add external microbes to it. And then we measure again how it will develop. And usually we succeed then by enriching the composition by the microbes we want to have in there. So this would allow somebody also to have a look whether local microbes are digesting better than certain other microbes. We know that certain species are better in degradation of certain feedstocks than others. But it can be, and usually it is the case, that if you have local side streams, the local organisms that are from that region are much better adapted due to evolution on degrading this, because this also happens all in nature, what we do in the fermenter. It just takes much longer and you have the emissions into the atmosphere. So they are adapted to this particular feedstock and they are eventually then more efficient than certain other microbes.
And I guess whenever you have a new microorganism, you always have to do the entire study, right? See how well it works. I mean, you have to start from basically from zero.
Yes.
Okay.
And this is also an aim to get faster, because you have to adapt these digestion process more to the local feedstock, and this means to the local whatever is there. And to get an evaluation just much faster than right now is one major challenge we have to solve within the next years. Some has already been achieved also by others, but we need to be even faster, cheaper, and more reliable on the data we get.
Daniela, do you wanna?
Yes, thank you, Jose. Regarding now this last question, and well, when you do anaerobic digestion, you normally use the microorganisms that are present in the biomass and in the bio-wastes at the beginning, especially before you do bioaugmentation so you will have these microorganisms involved in your process from the beginning if you do conventional anaerobic digestion plants, commissioning and ramping up. But I would think that, for example, these microorganisms for the highlands would be good adapted, for example, for low temperatures. So they would be working pretty well at temperatures between 15, 25 degrees, maybe better than others that are used to working at 35 degrees because the conditions at the Paramour are, especially at night, very high fluctuations in temperatures like desert climate. So they will be better adapted as Stefan commented. But obviously, it depends, and it will depend on how you work it. And bioaugmentation is a very, very interesting form of really optimizing the mixture you have in a reactor. I had also a couple of questions. I have many questions, but I will focus now on two questions. The first one is, you showed us at the end the plug flow reactor, and it was a very small diameter. And so I was wondering how you manage the solid contents in your mixture, because in anaerobic digestion, you normally have suspended solids within your reactant mixture. So how much solid content do you manage in your plug flow reactor, and how do you work so that you don't have blockage in the plug flow?
Yeah, so it's for the liquid phase is 10 to 12 liters. The size we cut down all to 1 centimeter. So no particle is greater than 1 centimeter. Mm-hmm. We have dry masses. We have now around 20% of dry mass. I would say we see already gradients from 12% of dry mass on.
So pretty high contents.
Yeah. That's for plug flow. Yeah, for plug. So So for vessels, we also do experiments in steer tanks. So in steer tanks, we have 5 to 8% of dry mass. And in the plug flow reactors, we have 12 to 20.
Yes, it's dry fermentation is pretty much dry phase. And you worked also, you talked us about
sorry, I have to, so we still have a liquid phase, and we have also a little bit of separation. So on the upper part, the dry mass is a little bit lower. So we're still all covering with liquid, but so all above 20, I would say, yeah, this would then not be any more liquid fermentation, but a solid phase fermentation. This is why we also stop at 20.
Okay. Thank you. Thank you, Stefan. And you mentioned that in the hydrolysis, in one of the first slides, that in the hydrolysis, you're working with 30 to 40 days residence time. Was I right, or didn't I get it right? Because it's pretty high, 30 to 40 days. Or was it on the overall process?
In practice, yes. In practice, yes. Yeah. I mean, here we are using less time because we are cutting down the substrate, so the degradation is faster. Here we are around 3 weeks, so to say. But in industrial scale, it's between 30 and 40 days for most of the biogas plants I know. Sometimes even 60 days in one single fermenter.
One single stage. And for two stage fermenter, only for the hydrolysis? What would you recommend?
Sorry, I didn't get your question. So you mean, no, for the hydrolysis stage, there are not many biogas plants having a separated hydrolysis stage, and there it's much faster. So hydrolysis is between 10 and 12 days in industrial scale, I would say. And then the first digester has a residence time of 30 to 40 days, sometimes even 60. And then the post digester has at least 30 days, but sometimes even 3 months. It's just to get out whatever is left. Yeah.
Right. Right. Very nice. That were my questions. Thank you.
Well, let's see if anyone has any other question. If not, you can also open your microphones if you want to ask. So, Stefan, we thank you very much for your wonderful presentation, and we thank everybody for attending. Remember that we have very soon next. I'm trying to find. I'm getting a little bit of problems with this. Remember, we have on September 4th, we have our next talk by Borja Velasquez from Spain. So please, we're going to be posting the art very soon. We already have a preliminary one, but I don't want to show it right now. So be vigilant of our social networks. I'm sorry, I'm getting entangled between Spanish and English. So thank you very much for coming, and we will see you soon.
Thanks a lot to everybody, also from my side. It was great to attend.
Thank you, Stefan.
Thank you very much,
Very good presentation.
Gracias. Hasta luego.
Thank you.
Thank you.
Bye.
Bye. Thank you.
Bye.